In this video, we're going to take a more in-depth look at the properties of gases, the compressibility of gases, and factors that affect gas pressure. So compressibility is the measure of how much the volume of a gas can be decreased when a force is applied. When put under pressure, how much does that volume shrink down? We take advantage of this property of compressibility with things like an airbag. So when your car gets hit in the bumper, there are sensors that measure the amount of force that is there when you get into an accident, causing a reaction to go off, filling up your airbag with nitrogen gas. Since the gas particles don't want to be together, but there's lots of empty space between them, as those molecules get pushed on top of each other and shrunk down into a smaller space which they don't want to be in, it absorbs energy, slowing you down over a much longer period of time, resulting in a lower force needed and causing you to be under less force, therefore less damage done to you during an accident. Here we see that looks like on the molecular level, we have the airbag as it fills up and those molecules being all spread apart as we see on the left, and then when you are thrown into the airbag and it squishes those particles into each other, occupying less space, the emptiness between them shrinks up, the size of the particles can't change, so therefore they get closer and closer together, and it makes it more and more difficult to push them closer together because they don't want to be near each other, and again slow you down over a much longer period of time. Again, this compressibility is due to the fact that there's so much empty space between these particles. Gases don't really have much attraction for each other. There's so little, we ignore it, and there's all that empty space between those gas particles, allowing those particles to then be pushed up on top of each other. Again, there's about 10 times their diameter in space between them in every direction. Again, looking at that 1 mole of water vapor, 1 mole of a gas takes, again, 22.4 liters, so it's really spread apart. But then if I were to take that same 1 mole of water and condense it to a liquid, now it's going to shrink down to just 18 millimeters of volume. So it's from 22.4 liters to 18 milliliters, again, cutting by about a power of 1,000. Again, that power of 1,000 coming from the x-axis, the y-axis, and the z-axis. Those 10 times their diameter apart from each other, 10 to the third 1,000. So there's 3 different factors that affect gas pressure. We'll look at them more in depth in a minute. But those 3 factors are the amount of gas, we look at in terms of moles, the volume, we'll look at that in terms of liters, and the temperature, and we'll look at temperature in terms of Kelvin. So how does the amount of gas, how many moles of gas there are, affect gas pressure? So think of filling up a raft. When you fill up a raft with air, you're pumping more air into the raft. As you put more air in, we know the pressure inside that raft increases because you have a pretty fixed volume of the raft. I know the rubber that makes up that raft can expand a little bit for the most part, though the actual volume of that raft is a fixed amount, and therefore by putting more and more gas in, the pressure increases inside that raft. So by putting those more particles in, you end up with more collisions. More collisions means more force means more pressure, and we see that with that raft. Again, putting more particles in, causing there to be more moles of that gas, because that 1 mole is 6.02 times 10 to the 23rd particles. So if I was double that, and I get double the amount of particles, I get double the amount of pressure. There's a direct relationship between the amount of gas and the pressure. Doubling the amount of particles will double the pressure because it's going to double the collisions and double the force that's going on. And we see, though, when we have a contained gas, and if it is in an environment that allows particles to flow, like if you think of a cell in biology, where you have water moving in and out of the cell, and as you take in food, it tries to balance out the concentration inside and outside the cell. The same thing happens with gases. They like to be balanced out. Gases always move from areas of high pressure to low pressure. We see that with weather systems. We see it with aerosol cans. The reason why aerosol cans work is because when you push down on the button and it now allows a passageway between, air will escape out, therefore lowering the pressure inside the can to then get to the point where it will equal the outside part of the can. Same thing when you pop a tire or you pop a balloon. Air comes rushing out because the pressure inside the balloon or inside that tire is greater than the pressure outside. So we say here with this football, again, putting more particles of air into the football is going to increase the pressure. As we pump more and more in, or as we see on the right, as air escapes out, then the pressure is going to have a direct proportion to the number of particles to the amount of pressure there is inside of that ball. Again, here we see that aerosol can. We have a spray paint can of yellow paint, and when I push down the button, allowing the paint to be propelled out at the bottom of that straw because of the gas pressure up above that liquid. That's why it doesn't work so upside down either, because now that straw is going to be up where the gas is, and then when the gas is going to come out, not the paint. But if you keep it upright, and eventually it's going to expel all the liquid inside, and the gas is going to now be allowed to expand a little bit, and the pressure will then be released, and eventually, once all the paint's gone, then even more of that gas that's inside there comes out. Then the pressure inside the can will equal the pressure outside, and that's when the can doesn't work anymore. It's one thing you have to be really careful of, because that can isn't actually empty. They put that can and throw it into a fire, well, that can's going to explode, because now you're going to heat up the gas inside that container, and now the pressure inside again is going to increase. And we'll discuss how, again, temperature is going to affect the pressure of a gas in one moment. But first we're going to take a look and see how volume affects pressure. Well, how does volume affect pressure? Pressure is the measure of force over an area, and as the volume changes, the surface area is going to change. So by decreasing the volume, it's going to decrease the surface area, and I'm going to divide by a smaller amount of area, resulting in a greater pressure. Conversely, as volume increases, the surface area increases, divided by a larger number, lowering the amount of pressure. So they are inversely related. So we see this with a bed of nails. Like, this works because all those nails, the surface area of all those points added all together ends up being not a whole lot different than just laying on the bed itself, as opposed to just stepping on a nail that goes right through your foot, because you only have that one pinpoint of area that is going to result in all of your weight on that one small area. Conversely, in a bed of nails, again, is spread out over a lot of little areas that sum together to be quite a bit. So this is kind of a common thing you see with you walking across your lawn. In sneakers, you have no problem walking across the lawn, not an issue at all. However, now when it becomes prom day and you want to take pictures out in front and you're wearing your nice, beautiful high heels, well, now your high heel sinks down to the lawn. It's not because you gained weight going from your sneakers to your heels. It's because the amount of area of your heels has since changed. And now if I have a same amount of weight, same amount of force, but much less area, it creates a lot more pressure, is what makes it slip on through. Conversely, when you try to walk through snow with your sneakers on, that doesn't work out so well. But when I put on snowshoes, then I can walk right on top, because now I'm going to increase the amount of area again, and where my sneakers would sink on down through the snow, by increasing my amount of area but having the same weight, the pressure decreases, allowing me to walk on top. Also, you can see how they are affected here with these pistons. On the left, where the volume is larger than on the right, but the same amount of gas particles, we see that manometer reading a much lower level on the left, because those particles are more spread out, resulting in less collisions due to the amount of space they have, having less pressure. Conversely, on the right, when they get squashed on down, well, now those same amount of particles in a much smaller space are going to collide with the walls of the container much more often, resulting in a greater amount of pressure due to the amount of force that's being applied to the walls of the container as they collide. And lastly, temperature. How does temperature affect pressure? Well, increasing the temperature is going to increase the amount of kinetic energy. Those particles will begin moving faster. And if they move faster, they're going to collide more often and with more force. So therefore, you're going to get much more force applied to the walls of the container. So there's a direct relationship between the temperature and the amount of pressure. Again, because the particles will move faster, resulting in those more collisions and also with a greater force when they do collide. We see that with a soda can. When you take a soda can, you put a little water in the soda can and you heat it up, and that water begins to boil. So now you have 212 degree steam inside that can. But you take it, you flip it upside down, and really quickly put it into water. Well, when the can was open, the pressure inside and outside were equal, so that 212 degree steam or water vapor inside that can was going to be the same pressure as the atmospheric pressure, and that's why the can doesn't explode. If it had been closed off and you heat it up, then that's when it would rupture and explode, and that gas would come flying on out. However, since it was open, it allowed the pressure inside to equal the pressure outside. But once you flipped it upside down and then put that same soda can, the same external pressure on it, as you see those arrows haven't changed, the same amount of pressure on both sides, but now when it's upside down inside the water, it's enclosed, the gas can't move in and out as freely, and that gas inside there, that water vapor inside there, cools down, creating less pressure inside, and now I have a greater pressure outside than I do inside the can, causing it to collapse on down.